From ContainerDays Hamburg, this video is proudly presented by Dux IT.
Yeah, it's really nice to see so many young people coming to a mainframe talk, because usually when you think about mainframes, the terms that would typically come to mind are old and expensive, outdated, complicated. But you most likely wouldn't really think about them in a cloud-native context. And hopefully I can convince you today that mainframes are actually indeed still relevant for some use cases. And they also have their place in the cloud-native and Linux world. So here are the questions I would like to answer for you today. First of all, let's get a common understanding of what mainframes really are, because if you don't work with them, you probably don't really have a proper overview. We'll talk about whether they actually still matter, how they work, and then most importantly, why would you even put containers on them in the first place? And then we'll deep dive into how to put them on there. So aren't mainframes legacy infrastructure? Yeah, but also no, and I'll explain why. So yes, they are legacy because they've been around since the 1950s. They still run COBOL. They're often tied to these old school institutions like banks, governments, insurance companies. And a lot of their workloads were written decades ago, and they're still running completely untouched. They're not really trendy at all. They don't fit the modern move fast and break things kind of mentality. But also no, because they're still evolving actually, and modern mainframes can run Linux. They support cloud integration. They have things like AI accelerators on a chip, and they can still process absurd amounts of data with way better efficiency and reliability than huge racks of x86 servers. And the companies that need that kind of crazy reliability, security, and just raw transaction power, they're still buying new mainframes nowadays. They're not going away. They're just kind of invisible because they just work and they're not as hyped as some of the other technologies. But aren't they just big, expensive servers? Well, not exactly. They're more like the computing equivalent of a nuclear bunker. So in essence, they are ultra reliable, high throughput, disaster-proof computers. But on the other hand, they're super specialized. So IBM actually tests their components against earthquakes and radiation, so they can withstand solar flares. So when we're all dead, the mainframes will still be going on, basically. And they've also been the source of a lot of hardware innovation. So IBM mainframes were actually the first enterprise appliance back in the day to support water cooling. And the in-joke used to be that if you have a problem with your mainframe, you have to call a plumber and not a technician. And their hardware, firmware, and OS are so finely tuned to each other, and they're built for mission-critical workloads. And those are just impractical to handle on some of these distributed systems. The most common use cases really are credit card transactions or withdrawing money at an ATM, where you don't want to wait for 30 seconds or something, where these small transaction times actually matter. I brought some numbers to prove this to you. So actually 90% of all credit card transactions are still handled by mainframes. And 71% of Fortune 500 companies use them. And they account for almost 70% of all production workloads, while just accounting for a fraction of the cost. OK, so I hope we've established a very basic common understanding of what mainframes are, and agree that they still matter at least somewhat. But how do they actually work, and what makes them so special? So we touched on it in a little bit. On the hardware level, all the components are super finely tuned to work with each other with super low latency. For x86 servers, you have to leave the chip oftentimes to make certain transactions. And these mainframe chips are the size of the palm of your hand, basically. And they can do a lot of transactions on the chip. And that means you have nanosecond latency instead of microsecond latency, which is a pretty big difference. And yeah, in terms of hardware, they can also do other crazy things. Like you can actually hot swap the CPUs while the thing is running, and the mainframe doesn't care. And the SLAs they build the mainframes for is 7 nines, and that's equivalent to a 3-second downtime per year, which is also quite crazy. And they have cool things like onboard crypto modules that are like HSMs and just onboard, yeah. And then on the systems level, the key takeaway is really that you can run all kinds of different workloads on them, either natively or virtualized. And depending on the hypervisor technology, you can really do so with practically no overhead. Just to give you some examples here in the diagram, we have some KVM workloads running on Z. We have ZVM, which is the IBM-specific hypervisor. We have ZOS, of course, for the more native and legacy stuff. And then finally, we have Linux on LPARs. And an LPAR is basically a logical partition of compute in the mainframe, which for simplicity's sake also kind of behaves like a virtual machine, except it's below the hypervisor layer and closer to the bare metal. Okay, now we have a basic understanding of how they work, and we'll make the jump to containers. So why would you want to run containers on a mainframe? So there are a number of different reasons, and one of them is if you want to modernize legacy apps, it makes sense to also add newer things onto the old hardware if you want to keep some of the like microsecond latency that you have when you're running the old school COBOL stuff next to modern things. Security and isolation is a big topic. And for some people, it's also just a cloud alternative with the whole data sovereignty stuff that is becoming more relevant again. You can have cloud-like agility without really leaving your data center if you run containers on these expensive machines that you already have in your data center anyways. The specific use case I'm working on is using confidential containers. So using OpenShift Sandbox, which is the downstream product of Kata containers you might have heard of. And yeah, Kata containers are basically just containers that run inside of a tiny confidential VM. And it's using the hardware-backed trusted execution environments of the processor. Why is this even necessary? Why do confidential containers matter? So normal containers aren't really super isolated. I think Dan Walsh has really famously said containers don't contain. It's just a process running on your machine. Yeah, and because you share the kernel and you trust the host implicitly, you have some isolation issues just by design. And Kata kind of fixes this by running each container inside of a lightweight virtual machine. And if you add in the confidential computing technology, you then have confidential containers. And yeah, it's a machine that the host then can't peek into, even if it's compromised. Just conceptually, Kata is made up of 3 core components. And one of them is the actual confidential computing part with this CPU level features used to encrypt the memory and block the host access. The attestation part, which verifies the workload owner. And then finally, the encrypted image pools and file system, just to make sure the images and secrets can only be decrypted inside the trusted execution environment. And yeah, for my use case, I was using IBM HyperProtect secure enclaves, which are a CPU level feature of the mainframe. And it has this hardware-based isolation and firmware level crypto modules that it's using to do everything on one device, because usually you'd have a separate environment to handle the attestation as a trust anchor external to your main workload cluster. Okay, so how do you actually put containers on the mainframe? there are a number of different ways. You could technically run them natively on ZOS with container extensions, which is a product I found out about while I was working on the project. And it's actually Docker Swarm under the hood, which is really wild to me that this is part of that. But I'll, of course, tell you about different ways using Kubernetes because I'm a Kubernetes person. One quick detour, just because a big differentiator on the software side of things and a bit of an initial hurdle is the system architecture. Do you remember when the Macs, the new Apple Silicon Macs were coming out and a lot of stuff just didn't run on them, just like Docker, and to some extent still doesn't completely run? It's kind of like that. So the S390 architecture used by Mainframes has some fundamental differences. The first draft of this slide was just a table comparing the two architectures. I found that really boring, so we're doing an animal analogy actually to explain this a little bit. So the octopus is actually a really cool animal. Did you know that if you cut off an arm, it can just regrow it over time? It's kind of like a mainframe because it has like this insane parallelism in it. It can have like this crazy fault tolerance, and it just recovers like that. And x86 is not quite that cool sometimes because I'm comparing it to like a domesticated raccoon. It can do a lot of things at once, but it'll probably break something in the process. And if you cut off an arm, then you have to take it to the vet. So yeah, the first scenario I tried out was using ZVM worker and just a regular bare metal x86 Kubernetes cluster. And that's easy, right? It's just another Linux machine. You install some packages, you enable some systemd units, and we'll join the cluster. Yeah, that was actually a lot easier than I expected in the beginning. So yeah, this is an example with this vanilla Kubernetes on Ubuntu bare metal hosts and Ubuntu ZVM. And the only real challenges to get this to work were deploying the CNI to be multi-arch and just adding some labels to the nodes. But yeah, here we can see some workloads running on there with the S390 architecture. But the second way I've done it is almost the same scenario, but using an LPAR worker and an OpenShift cluster. And you'd think it would work kind of the same way. But yeah, it's easy, right? No, so there are two fundamental differences, and they're kind of related to each other, and there are reasons why it didn't work quite as easily. So the first reason is that OpenShift uses CoreOS for their host, which is nowadays this Red Hat Enterprise Linux, but meant to be immutable and optimized to run containers. And the second reason is that LPARs hate me, which means that they're very particular about how they will boot or not boot an operating system. Let me explain that. So if we're just using a regular off-the-rack ISO and try to boot something in an LPAR, it actually won't work. Nothing will really happen because we need two specific files for it to work. There's the instructions file, which specifies the kernel, the initial RAM disk, and links to an instructions file. And it has some memory load addresses as well. And then the parameters file, which is just a lot of boot parameters required to start. And it contains things like the ignition, which partitions the drives and then sets up networking, and a bunch of other things to then eventually join the cluster. Yeah, and I've always kind of described this parameters file as this collection of ancient runes that have to be in the right combination for the thing to work. And a lot of it wasn't really documented at all, so it was a lot of trial and error to get that to work. And actually, CoreOS release had a bug in it, which threw me off initially. I'm wondering if anyone can spot it on this slide. Okay, so actually the paths here, they don't line up. So it's searching for files in a directory where they actually don't exist. That was an issue since 2020. And I talked to the developers, and apparently it only affects CoreOS on LPAR, and I was the first one to ever try booting that. So yeah. I'll briefly talk about some of the parameters mentioned in the PRM file, and I'm sprinkling in some cats just to keep your attention, and don't worry, we're not going over all of them. So on the networking side, we have this IP parameter, which is fairly basic. It's just the static IP, netmask, hostname, and the interface. This creates the VLAN interface on the network controller. This is the driver used by these OSA cards. This just enables Ethernet mode for the container networking. And then for storage, this configures fiber channel protocol. This aggregates all the fiber channel paths into a single device. And then finally, this installs CoreOS to this multipath device. There are a lot more, but I think those are the least arcane ones that we can talk about here. So once we have a working ISO and some configuration files that we set up, how do we get it into the mainframe? So you don't have to actually drive to the data center. Actually, I was really hoping for that because I wanted to see the thing in real life. But there's an HMC or hardware management console. It's kind of like a BMC for a regular server. And at first, we had firewall issues, so we couldn't use SFTP, and we had to just manually select the file from our PC and then upload it to the HMC over a VPN, which took forever. And if you're trying to move fast and iterate with these parameters, because the thing just won't boot, it's really painful. So yeah, SFTP is recommended. And we did eventually get the network to play nice, and we could just load the boot files over SFTP. Okay, so what we have here is like the general setup required to boot. So we have the initial server on the first boot. The server will, or the cluster will read its configuration from a source of truth, and it will apply that configuration. And normally you can just read it from the existing cluster, but we had to patch a lot of things in the ignition to make it work. So I wrote a custom systemd service to handle some certificate trust issues. And I also put in my SSH key just so I could connect to the LPAR and troubleshoot because things just weren't working in the initial join process. So yeah, the actual initial boot files were served from an HTTP server. And yeah, the install target, yeah, those are the files from the HTTP server. And the install target in the end is the storage system, which is attached to the mainframe. Yes. And these diagrams can get a little abstract. So this is what it looks like in real life. I did actually get to see, I didn't realize I got to go to the data center. So on the left side, we have the HMC that is on top of the mainframe. It's the mainframe from behind, by the way. It doesn't look quite, it looks a lot prettier from the front. And then in the middle is the storage system. So it's the fiber channel stuff that is connected to the mainframe with these blue wires. And I didn't think about that when I was in the data center, but so it's a little cut off. But there's another rack of x86 servers that host the jump host and other components on the right of that. Okay, so we have everything in place for the system to boot, and now we can observe the install process from this beautiful modern console. And after the initial installation, we just need to change the boot source from SFTP to the storage system and reboot, kind of like when you install something at home, you take the USB out and then boot normally from disk. And then with those hurdles overcome, we just get a normal certificate signing request like we do get normally when a node wants to join the cluster. There are still things that can go wrong here, where like daemon sets aren't starting properly, but those are all things that you can fix by setting the correct kernel parameters. Yeah, and equipped with that knowledge and experience, we can actually put workloads onto this new S390 node. And yay, it works. Yeah, just to wrap some of the things up that we learned today. We learned what mainframes are, established that they at least still matter somewhat, and went over why you would put containers on them, and explored some ways to put containers on them. So what's next? Maybe this got some of you interested in trying out, like tinkering with mainframes on your own. There is the Open Mainframe project that is an initiative by the Linux Foundation, which I find really helpful. There are some projects like the thing in the middle, the Linux One Community Cloud. Yeah, you might say, I don't have a mainframe at home. How am I going to replicate some of these things? You can actually get a mainframe. Well, you can get a ZVM to play around with from this community cloud. There is the Ambitus project that works on porting FOSS stuff to mainframe architecture. And yeah, there's also the sandbox containers documentation if you're more interested in that. I mentioned that the documentation was really bad. I fixed it. This should be coming out soon. So if you're interested in doing what I did, there's a learning path on Red Hat Developer. And yeah, it should be, I think it's still being reviewed. It should be coming out very soon. Yeah, I think we can do Q&A now.
How did you get into the whole working with mainframes thing? Because this is like the first time I met a person that works with mainframes.
That's a good question. Yeah, people are usually a lot older and have been doing it for a lot longer. So I work in consulting, and someone just asked who wants to do this mainframe thing, and I've always been really into systems, like low-level system stuff, and I was like, sure, I'll try. I'll do mainframe.
That's a really nice story. I think there are some questions. Let me read them out for you. After all you went through, which method to deploy containers would you prefer?
Or which method to deploy containers? Oh, it depends on the use case, really. I don't think I would run my home lab on a mainframe. I don't really have a reason to. But the project I did this for was a hyperscaler customer, and they're really focused on this whole digital sovereignty and confidential computing stuff. So yeah, it does make sense for some use cases, probably not for most of us.
The next question is, how good was the integration of Kata with the mainframe hypervisor?
It's actually, there'll be a follow-up blog post to this actually for this part, because the mainframe we were using had an older version of the firmware, and it didn't support quite what we were looking to do. So we had to deploy another LPAR using running rel, just regular rel. and using the peer pod pattern. And because the rel host can install libvirt and CoreOS doesn't have the kernel modules for virtualization on top. And then kata uses the rel lpar to actually run the containers on there, the micro VMs.
Okay. Next question is, I saw it was used as a worker node. Can we assume it can work as a master or a compact master worker?
Yes, yeah, you can assign any node role to it. You can also deploy non-hybrid architecture clusters, so like complete S390 clusters on there. It's arguably easier because you don't have to deal with all the multi-arch stuff. But yeah, it works. And a common question there is also, wouldn't it make more sense to have the whole control plane on there because of the increased performance? And we're going to do some benchmarking on that. It's like been on my to-do list for months now, but I've never had the time to actually do the benchmarks. But yeah,
There was one other question, it disappeared. I'm not sure if it was like intentional, but I didn't like archive it. So is there a tangible benefit to doing attestation on a mainframe versus on x86? It's jumping around, I'm sorry, with confidential computing.
Well, having a self-contained system doing it is kind of the main benefit here, and using the onboard crypto modules. And yeah, that's the use case the customer wanted.
Okay, give me a second. There are so many all the time. A learning path is only 45 minutes for this? Or like, is 45 minutes for this?
Well, if everything works.
Okay, there's another one. Is it correct that containers are part only in mainframe VM and not directly accessible in the TN3270 console? I'm so sorry.
Yes, yeah, they're not directly accessible through that. Yeah.
And the last thing that Lisa submitted is quick feedback, really great, and entertaining talk and slides.
Thank you.
So big round of applause.
Thank you.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.